Thank you. Yeah, Morgan Chidester. My last name is weird. I wanted to thank the previous speakers, especially JJ. He gave a very nice intro on white dwarf seismology, so I'll kind of be gleaning off of that quite a bit in this talk. And today I'll be talking to you about trapped modes in variable white dwarfs as probes of the C12 alpha gamma reaction rate. So just keep in mind, this is all theory stuff. We got some exciting observation. Now we're on the theory side. So I wanted to start by kind of reminding ourselves why we care so much about the C12 alpha gamma reaction. And this was kind of touched on yesterday by the first speaker, Maurizio. But during the helium burning phases in stellar evolution, there's two important reactions, the triple alpha and the C12 alpha gamma reaction. And those two reactions ultimately determine, one, the carbon to oxygen ratio in the universe, which has biological implications for life, and the CO stratification for carbon-oxygen white dwarfs. So these rates are important. Now, the triple alpha has a, rate uncertainty of 10%, but the C12 alpha gamma is around the 50% level. This is problematic because we want the rates to be compatible with one another when we're trying to understand this ratio and carbon-oxygen white dwarfs. So we need to constrain this rate. And one of the ways you can do that is through white dwarf seismology. So I'm going to just mention some previous work that's been done in this vein. There's probably more than this. We've actually heard some from other talks, but I'll just mention these three. Kind of the idea is to vary the C12 alpha gamma rate and see how that impacts the resulting white dwarfs. And collectively, these three found that when they varied the rate, it impacted the white dwarf chemical profiles, the structure, evolution history, and the pulsation spectrum. So kind of the novelty of the work that I'll present today is that we found a new pulsation signature for the C12 alpha gamma rate that has not been identified previously. So how we did that is going to be described here. But first we, oh, is that showing up? Yeah. Hopefully that's not blurry to you guys. Anyway, we started by spanning the current probability distribution function for the rate. And this was taken from De Boyer et al. 2017, which was improved this year by Meta. And this data is publicly available on Zenodo. So what this figure is showing you is the reaction rate ratio with respect to the nominal value of sigma 0. And sigma here represents a standard deviation away from the nominal rate. And I spans from -3 to +3 sigma in half sigma steps as designated by each one of those dotted curves. The gray curves show negative sigmas, the green curves show positive sigmas, and the color fades the further away you get from sigma 0. So that'll be consistent throughout the presentation. Now, spanning the PDF like this gave us 13 specific rates, which we constructed 13 models from and evolved them from the pre-main sequence to cool white dwarfs. They all began with the same mass, the same metallicity, they just differed in sigma sub I. Once they reached the white dwarf cooling track, we used the gyre oscillation code to track pulsations. And so just again, this is the input rates. And on the right, we have the output mass fraction profiles for all of our models. And you're probably all kind of used to seeing this type of a figure. So I'll just kind of highlight the important points. But first, we have this inner part of the core, which we label R1. And immediately you can see that the input rates show a very clear distinguishment in the resulting oxygen and carbon profiles, which is fairly intuitive. So we can say that the C12 alpha gamma rate largely determines the structure of the profiles in this region. I want to mention that this region is sensitive to the convective mixing that's prescribed on it. And yeah, Maurizio touched on that yesterday as well. So moving on to the second region is the outer part of the core, where carbon starts to dominate. And again, we see a clear distinguishing pattern between the input rates and the output mass fraction profiles for carbon and oxygen, which distinguishes sigma I. So you'll notice two things about this region. It's highlighted, and the profiles are not flat. That's because this region was determined in nearly purely radiative burning. So this region is mitigated from the impacts of convective mixing. So just keep that in mind. Moving on to this third region, we have the transition from the carbon to helium, carbon to helium transition, and the C12 alpha gamma ray impacts that transition. And the variations you see here in helium come from differences in their thermal pulse histories. So Pepper et al. Also agrees with this finding. They found the same thing, that the rate impacts the number of thermal pulses. And then lastly, we have the hydrogen envelope, and it doesn't appear that the rate strongly influences this. So the whole point of me going over this with you is to show that, okay, we have a distinguishment between the input rates and the output mass fraction profiles, as you would kind of expect. The question is there a seismic signature that will pick up this sigma sub I distinguishment? Oh, what did I do? Well, let's see. Sorry. Okay. Hopefully it keeps going. The last thing I'll say before moving on is these regions have been designated by their composition gradients. That's because in doing so, they can create resonant cavities for G modes. When a G mode resonates within one of those cavities, it can become trapped. And it turns out that trapped modes can be more informative of particular regions in the star than other G modes. So with that in mind, the punchline of this project is that we did indeed find a pulsation rate signature that came from the R2 trapped modes that distinguished sigma sub I. And that's shown globally in this figure. So the y-axis is the relative period change between the sigma sub I rate models and the sigma 0 rates for the R2 trap modes. The x-axis is model sequence type, which I'll elaborate on. But for now, I want to focus on this first column. First, you can see that there's a separation and distinguishing pattern between the rates and the resulting relative differences. Namely, that the negative sigmas had longer periods, the positive sigmas had shorter periods than the nominal value in a more or less well-defined pattern. I want to pause on this column because when we first looked at our pulsation results, this was the only G mode. It says G5, so radial order 5. This was the only one that showed this kind of distinguishment. And when we first got this, we were a little puzzled, like, what the heck? But when we investigated and saw that it was resonating with R2, it inferred that, okay, it really could be picking up that sigma sub I distinguishment. But we had to verify that across other model sequence types. So we did the same analysis with the 13 rates. We varied the masses. We varied the thickness of the envelope, whether they were DA or DB white dwarfs. And it turns out that our result persisted. I'm not sure if it's super clear, but the radial order does change across the model sequence type, like that's a 6, that's a 7. But what all of these G modes had in common was they were being trapped in R2. So what we can conclude is that R2 trap modes in white dwarfs might be an observable signal for the C12 alpha gamma rate. And this is a new probe. So if you are interested in further details, you can read about it. Oh my gosh. The last thing I'll say is, before moving on, observed white dwarf periods have sig figs out to 6 to 7 digits of precision. So the global relative differences of around 2% are within the detectable regime. Now I'm going to talk a little bit more on some preliminary work for next steps. So as Maurizio mentioned yesterday, the white dwarf structure can be sensitive to mixing and thermal pulses. And I mentioned that our R2 magic region was great because it was mitigated from those effects. However, the edges will be impacted from overshooting, core overshooting, and the thermal pulse history. So we decided to look into that. And this is just preliminary work, but we first decided to fix the right edge of the R2 region. And how we did that is we stopped the models at the first thermal pulse. Before we added core overshooting, we just wanted to see and make sure that our seismic signature persisted. And it turns out that it did, but we got an additional seismic signal coming from G2. G2 wasn't necessarily trapped, but it was weighted most in the R2 and R3 regions, so it could still be picking up that sigma sub I distinguishment. That being said, we then added a little bit of core overshooting, and this is the resulting profiles. You can see that the abundances were impacted when overshooting was included, as well as this left edge of R2. Now, when we look at our seismic signatures, this top one is the G2 one. The y-axis is the percent differences, the x-axis is sigma sub I, and we still have a very beautiful pattern with the distinguishment in sigma sub I. So it persists even with our added core overshoot, given it's a small value, but more to be explored. Our R2 trap mode results are here, and that linear pattern is disrupted. That's not to say that this isn't a great signature, but we have to do more investigation to understand, okay, what is the pattern of the R2 trap mode when we include overshoot? So I look forward to your questions because maybe you have more insights on this work. But thank you very much for listening, and I will take your questions.
Thank you. Questions? JJ?
Yeah, thanks, Morgan. Great. Do you have a handle on what is the highest radial order that is affected by these changes? How high did you go, and were they all affected, or? That
is a good question. So yes, like I mentioned, when we looked at the full pulsation spectrum, we looked at G modes for radial orders up to 20.
Okay.
And L equals 1 and 2. The magnitude of the relative differences was within the detectable threshold throughout. But the trapped mode was the only one that showed a distinguishing trend for sigma sub I.
And the ones that were trapped were usually 4 to 6?
Yes. Okay. Yeah, it was in like the 2 to 7 range for our models.
Mm-hmm. Evan?
Yeah, so great talk, Morgan. This is a really interesting result. I'm wondering a little more about the left edge of this region that you care about, which Mauricio gave a really great overview of all the things that can go wrong. Is there a way to sort of parametrically explore, like moving that around, doing extra mixing? It also seems, degenerate with the amount of carbon oxygen you end up with. But how sensitive is the signal to extending that really much further out, say like what you might get from a breathing pulse?
Right, that is an excellent question. And that's kind of what's in the works. So with our little bit of overshooting, I don't know if this is clear, but that left edge did get pushed further out, which makes this R2 region a little bit shorter. R2 is definitely still there, but it's just shorter. As far as affecting the signature, I think we really have to resolve the thermal pulse history to see if this signature persists, because this is very viable. It kind of survived that added core overshoot, that disruption of the boundary, but this one definitely got disrupted. But yes, great question. We want to know too.
Another question? I have a short one. One thing that I work a little on this, and one thing that you find is that you can, let's say, simple words, you can reproduce the same profile if you change the carbon-oxygen reaction rate and the overshooting. It's like they pull in different directions. So you've given some thought on that?
Yes, so that's what we're exploring right now, is kind of that coupled uncertainty of, okay, what's the interplay of both core overshooting and changing the rate. Kind of our argument though is that even when you add overshooting, I mean, okay, if you add a very large value, it could disrupt like all the profiles, right? But within what you would expect,
reasonable values.
A reasonable value, this region should still persist because of that radiative burning. So.
Okay, thank you. Okay, we thank Morgan again. Thank you very much.